In this lesson, what kinds of questions or what would we learn? In this lesson, we would have a question, but this question is about the integration, an application of integration. But for this integration, we would have moment of inertia. In short form, we can write it as MOI. Okay? So, moment of inertia. Let's take a look at this question. So, this question, we'll have to find the moment of inertia of an ellipse with even mass distribution, semi-axis A and B, and mass M. And this ellipse, it has to rotate about this axis perpendicular to the plane of the ellipse and through the mass center. These types of questions, first thing, draw its graph. This is an ellipse. I drew out the axis X, Y, and Z to show this is on one plane, on plane X, Y, but its rotation axis is the Z. In the last lesson, we actually have already done this question, but in the last lesson, we have used two methods. Either you use Cartesian coordinates to recalculate or perpendicular theorem. Can we just try out the polar coordinates? Okay, that means we would have method number 3, polar coordinates. Let's find out. For this question, using polar coordinates, we're going to say here we take one part. This is an R. Now where is that theta? Is it R to X or is it R to Y? I think it will be from this R to the X. Like this. For polar coordinate, we have this R, we also have this theta. But then they didn't tell us semi-axis. Where is A? Where is B? A. Where can we put it? Maybe I want to put it on X. Then maybe B, I would want to put it on Y. Like this. We also have a locus equation for this ellipse. The locus equation is x squared over a squared, in this case, plus y squared over b squared is equal to 1. This is the locus equation. But you have to be careful. This locus equation is only for its edge. At the edge, that is the parameter. The locus equation is only for the parameter. Okay. But now why would we want this locus equation? So let me tell you. X and y. Well, we can get some of the things from it. Like, let's see, the polar equation, we also have x and y. What is x? What is y? Let's see, x. You need this part. We can make a right angle triangle. And then use all that we have learned in trigonal. Like for example, x. Now we can look at this part. Y. We can look at this part. X is a cosine. So it's a r cosine theta. Then y, that would be a r sine theta. Right? But then, would we need anything for these? Or can we sub them in? So for this part, they're together. Now can we just try to sub these in? Let's try. So what we'll have, we can take out our square from both of them. Okay, let me just write everything. First part here, x squared over a squared. Put this in, r squared cosine square theta over a squared. Then plus this part, y squared is the r squared sine square theta over b squared. And this is equal to 1. Therefore, these parts, we might want to take an r squared out of them and leave the rest inside first. Which will become like this. After that, less common denominator. Like this, then we can divide this whole thing, this whole fraction, to the other side. That means r squared would be a squared b squared over b squared cosine square theta plus a squared sine square theta. Okay? So these parts, let's find r. For this r, well, we'll need a square root on both sides, so there will be a positive, negative. Then AB, from square, you can just take them out. Over square root whatever's inside. Like this. So this is our r. For this r, okay, so we found it. But then, what others would we need? Let's see. So we have r. Then how about, for that we have m r squared. We know r. How about m? M, we need to change it into a dm because it's only for this little piece. dm. Let's find this. First thing, mass density. Mass density. mass over its area. Because I did just a 2D, if you say it's 3D, then that will be its volume. What is an area of an ellipse? So that will be pi AB. Now AB, A, half of its major axis, B, half of its minor axis. Well, we can say it like that. Different cases you can say it differently. Okay, m over pi AB. This is its mass density. Then we need its area. That this little piece it takes. For that, dx, dy. But dx, dy now we want polar coordinates. How come we have a Cartesian coordinate here? When you change that. So dx, dy, it would become an r, dr, d theta, like this. So right now we have dm, we also have r. Well, what do we want to start solving right now? Let's start. So we have I that is equal to, just by looking at this, you can see, we need to use the double integral, integrating it 2 times. Mass density, constant. We can just leave it on the outside. mr squared. Okay, we have r squared. Wait a second. R squared. Another r. R cubed. Then dr d theta. Okay. Then its range. Where is it? R. Of course, starting from mass center. So we can start from 0. But where does it end? Well, then let me tell you. We found it. It's right here. But positive, negative, we don't care. Why we don't care? We only want its length. We don't want, is it like in a positive direction or in a negative direction? We don't need. Like this, and then after that is the range for theta, because first we integrate with respect to r, then we integrate with respect to theta. But for this part, theta, you don't have to use the whole thing, because all these you can cut into 4 parts and they are all the same. So these 4 parts, we just need one of them. Let's say this part. That means it will be from 0 to half pi. But 0 to half pi is a quarter. So we need times 4. Okay? Then 4m over pi AB. Then this integrate from 0 to half pi. But then you integrate this part, r to the power of 4. Now, r to the power of 4, it would become 1/4 r to the power of 4. And you have to stop. R that is 0 to AB over square root b squared cosine square theta plus a square sine square theta. Like this. Next, four and a quarter simplified. 0 to half pi. After that, r to the power 4. Okay, 0, we don't need to care about that. This part, we need a to the power of 4, b to the power of 4 over this b square cosine square theta plus a square sine square theta. Then square again. At this part, it gets a little bit tricky now. But first, let's not use substitution first. We can first take this out. Yes, we can. It will become a cubed b cubed over pi. Then down here, we might want to take out, okay, let's say we write this square first. We take out a cosine square theta. After you have that square, that means the cosine to the power of 4 theta. Then cosine to the power of 4 in the denominator can become a secant to the power of 4 in the numerator. Then you have to over b square. Maybe I don't like the b square and a square inside. Let's see. I just want to take this out. Taking out a b square, perhaps. Or wait, but behind there will become a tangent. Maybe let's take out a square instead. So this part is left with b square over a square. This looks simple. Then tangent square. Now this also looks simple, so that later you won't have all the things at one place. Now at this part, can we use substitution? Okay. So let's try to use substitution. But then, secant, tangent is messing it up. It makes it confusing. Maybe I would want to try something else first. Let's simplify this part. Make it look simpler. Secant to the power of 4 theta. I would want to put two of them inside, become a tangent theta. But then, secant square theta is still there. But wait, now this only square. So I can change it into 1 plus tangent square theta? Yes, it's possible. Now it's more peaceful with only tangents here. So we can use substitution. What would we let? Now the tangent theta looks like a little bit. Now we don't like that. So we will want to let tangent theta, let's say, we let it be x. Now what is the range for x? Let's see. Theta, when it's at being 0, tangent 0 is a 0. It's a 0. Then, theta is half pi, you sub in half pi tangent, half pi is infinity. So you'll get 0 to infinity. Then how about this fraction there? Fractions. I want to change it. So I would also want to let P equals B over A. But P, let me just tell you, just a constant, because A and B, they're also constants. And this is just to make it become simpler. Okay. Now this part, wait, would we want a P for this part? Constant different, we don't need that. But then I realized a problem. How about d theta? Wait a second. If this is a d tangent theta, can we just change it into a dx? So is it true that d tangent theta is equal to a dx? Okay. So here we have a 1 plus x squared. Then I have to over, so this bracket, change that to a p squared. Then we have to plus x squared, then square again. This part, dx. Then next, what would we want? Well, this fraction, it looks like it's quite big. Maybe I would want to split it a little bit. And then we will use partial fractions. Partial fractions. For this, split it as plus. But then, front part, okay, let me just write this bigger. Front part, I want it to become like this. Make it simpler. Then the part at the back, if I have like this, that means I already have an x squared plus p squared. X squared we still need another one, but we don't want this p squared. That means we would have to plus, let's integrate from 0 to infinity, we'll have 1 minus a p squared. Like this. Is it alright? Well, yes, I can have this. The problem is this part. This part is making it a little bit difficult. Let's work it at one side. Let's work that out. So just use simple numbers to represent it. 1 minus p squared, we don't need to care, it's just a constant. So what part we need is only, let's say, the simplest alphabet A. Then we'll have a bracket a squared plus x squared, bracket square. So we'll work this part out. But then for this part, this would be equal to, okay, 0 to infinity, but then that x squared there, together with an a squared there, we don't like them together. I might want an a squared outside. Do you think so? Let's try it. So we can let x be equal to a tangent theta. A tangent theta. Okay. Then dx, it would be equal to a tangent will become secant square theta. Then theta is range. X is 0. Tangent inside the theta would be a 0. Like this, then it would be all the way to infinity. A, no way to be infinity. So we have to make tangent theta an infinity. Then to make that an infinity, theta will now go to half pi. Like this. That means A secant square theta is at the numerator. Then you have to over A square plus, wait, another A square. Take that out, A to the power of 4. But inside we'll have 1 plus tangent square theta. That will change into a secant square theta. But then square again. That makes secant to the power of 4 theta. Then d theta. Am I right? Then simplification. Like this. Wait. I don't mean infinity is pi over 2, or otherwise known as half pi. Like this, then is right. Then 1 over secant square theta. Secant square theta is 1 over cosine square theta. That means it can just become a cosine square theta d theta. Like this. And then after that, this would be equal to 1 over a cubed, maybe double angle formula, another half, 0 to half pi. Inside, that will become 1 plus cosine 2 theta. Now it's very clear what is the answer, because the part at the back, cosine 2 theta, definitely becomes sine 2 theta. Then if it becomes sine 2 theta, sine pi, 0. Sine 0, still a 0. So we just need to look at a 1. That would become half pi. Half pi times this. Pi over 4a cubed. This is the answer for this part. So we can put it in here right now. This part in front, change it to a tangent by using our basic formula. Wait, we already integrated. Extra p, 1 over p. Then we have tangent. Is it an inverse tangent, or that is an inverse tangent? X over p or p over x? X over p. After that, start from, what do we want? 0 to infinity, right? Okay. Plus this part. Then we change it into a square bracket. Since we have bracket 1 minus p squared times that thing. But we have to be careful. This is a p cube. Why is it a p cube? This part we use a, so that's why it's an a. But this part we use a p, so it's a p. It will become like this. After that, well, this part, if it's having infinity, inverse tangent infinity is a half pi. If it's having 0, inverse tangent 0, 0. Then you have to plus Let's just put this part the same first. Then P, we'll change it back into B over A. So change it back into B over A, that's a A pi over 2B. Then we have to plus. We can common denominator this part. P squared is a B squared over A squared. So B squared over A squared, common denominator is an A squared. That will become a A squared minus a B squared. For this part we don't need. Then times a pi over this. Now this part, B cubed, then above we'll have an extra A cubed. Like this. And then simplify times it together. Wait, this is a minus B squared. Then I have to over 4B cubed, and you also have a pi there. Okay, like this, you'll realize both of them have A pi. A pi, simplify. Next up, you might want to times a B cubed inside. Yeah, and this 4, 2, very annoying. Take a quarter of them out. So you'll get a M over 4 after that inside. A pi simplified. 1 over B becomes a B squared. Then I had to plus this part. Wait, but then you have an extra 2 because of this. A pi, no more. This part, okay, B cubed, 4, also no more. So then it's just a plus A squared minus B squared. Minus becomes a B squared. So it's a M over 4 bracket A squared plus B squared. It's like this. So that means this time we can end here. So for this, let me tell you what types of things have we used. First part for that, locus equation. For this boundary, it's a locus equation. Then inside here, just that we find the M, and then using the using the MR square. Then this part is just integrate first, sub in. This part is actually factorization and then changing. How about this step or this step? Now we used this thing go back like secant square theta. It goes back. But then the other secant square theta, we use a trigonal identity. Okay, and that makes it become a 1 plus tangent square theta. After that, we use substitution. Then, okay, so this is just after substitution. Then partial fraction. Then we take one part out to integrate first. Then we also use a basic formula for integration. That gives us this inverse tangent. Then after that, it's just sub in, then just some calculations. Okay, so for this lesson, can we end here right now? Okay, so I hope you like this video. And if you like our videos, don't forget to subscribe to our channel, and thank you for your watching.